Welcome back, Chemistry 30. This is the first booklet in Unit 5, Equilibrium. It is Section 18.1, Equilibrium, a state of dynamic balance. And what we'll be looking at is what reversible reactions are, chemical equilibrium, law of chemical equilibrium, equilibrium constant, homogeneous versus heterogeneous equilibrium, recognize the characteristics of chemical equilibrium, discuss non-chemical analogies which illustrate or simulate equilibria, distinguish between dynamic equilibrium and steady state, analyze graphs of concentration or products with respect to time, write the equilibrium expression for systems that are not at equilibrium, calculate the equilibrium constant, interpret KEQ values, solve problems, etc. Okay? So first thing, the formation of ammonia. In the textbook they talk about the equilibrium of ammonia and nitrogen and hydrogen gas. It turns out it's a spontaneous reaction because we get a negative delta G value, and we talked about that in Unit 3. Number 2A, if nitrogen and hydrogen are placed in a closed container, what starts to happen? So if we imagine we have nitrogen and hydrogen, they slowly start to produce ammonia, NH3, because that is what the product is. And of course what happens is that NH3 goes back and produces nitrogen gas and hydrogen gas. So we start off with reactants, it starts to form products, and gradually products go back and form reactants until what happens is an equilibrium situation. So we have our reactants, which are nitrogen and hydrogen. Initially no products, but as reactants are used up, products are formed, and eventually they level out to a flat line. And that means that the concentrations are constant. Very similar to the little experiment or simulation that we did with the water and the grad cylinders. Initially we had water in one tube, we slowly transferred it to another, and to simulate a reversible reaction we put water back in using another straw, and eventually the volumes, they didn't become the same, they didn't become equal, they became constant. The level that they were at stayed constant. And that is true with concentration of reactants or products at equilibrium. So visually, we see that the concentrations are constant, or the volumes are constant with that water one. On a graph, a concentration versus time graph, we're looking for when they level out to a horizontal line. Okay, so that is an indication of equilibrium, when the forward reaction and reverse reaction are equal. So a reversible reaction, that was a case of a reversible reaction where reactants can form products and products can turn around and form reactants again. By looking at an equation, how can you determine whether or not we have a reversible reaction? Usually we use a double arrow, a double half arrow. So this means A forms B, and B can go back and form A. And this happens a lot with gases, reactants that are gases, products that are gases, they are definitely reversible. Because a lot of reactions aren't reversible. Frying an egg, for example, you can't get the original uncooked egg back, but there are reactions that are reversible. Okay, so as I mentioned, we looked at the volumes in the cylinders. The concentrations became constant. If we look at what else happened there with equilibrium, is that the volume in the straws. So no matter what straw you used in what cylinder, we had a wider straw and a thinner straw. Eventually what happens is that the volumes of liquid, due to the levels of the grad cylinders, became equal. So the fat straw here would have a lower level than the skinny straw. But you can see here the red liquid in each is the same. So the levels are different because of the diameter of the straws, but we get to a point where the forward reaction and the reverse reaction are the same, and that's what made the volume in the cylinders stay constant, because I was transporting the same water back and forth, the same volume. So the volume in the cylinders represents concentrations of reactant and product. They stay constant. The volume in the straws themselves represent the rates of forward and reverse reaction, which of course are equal. So, even though the concentrations are constant, the forward and reverse rates are equal. So the amount of A forming B is equal to the amount of B forming A. Even though I have different amounts of A and B, the amounts of A and B stay constant because I have an equal amount of forward reaction and reverse reaction. So back to the ammonia example. Summarize how placing nitrogen, and this should say hydrogen, in a closed container eventually reaches equilibrium. So if I take a look here, 1 nitrogen gas plus 3 hydrogen gas yields ammonia. So initially I would just have this present, my reactants, and I would have 0 products. And eventually some nitrogen and hydrogen combine to make ammonia. As ammonia is being made, some of the ammonia goes back and produces nitrogen and hydrogen until we get to a point when the forward rate and the reverse rate are equal. And when the reverse rate and forward rate are equal, that means I'll have a constant amount of nitrogen, hydrogen, and ammonia. If I was to look at a graph of that, let's take a couple of minutes here. So if I had, notice here I have a 3-to-1 ratio of hydrogen to nitrogen. So this could be hydrogen. So that's my H. Let's try to squeeze this in here. My nitrogen, it's a third as much. So I should have 3 times more hydrogen than nitrogen. So my nitrogen would be way down here, approximately a third. So that's my nitrogen. I'm going to have a hard time fitting this all in here. And initially I don't have ammonia, but as my reactants are being used up, I have a product being formed. And that could be ammonia. So you see how that works. Everything becomes level, constant at equilibrium due to an equal amount of reactants forming products and products forming reactants. So 3 times as much hydrogen as nitrogen as illustrated here. I'm trying to show that graphically. And then initially no ammonia, but it is formed as reactants get used up until eventually everything gets leveled out, equilibrium at around here where everything begins to flatline. Okay, so do we have to have equal amounts of products and reactants? No, but they are constant. So you see they're not the same level, they're not the same value, but they are flatlined, meaning constant. So we use the water in the cylinders as an example. Another example we could talk about is 2 cities that are separated by a bridge. So if we have a small city on this side that has 35,000 people, large city on the other side, 100,000 people, we could say first thing in the morning, people commute to work. The amount of people going from left to right is equal to the amount going from right to left. So this is the equal part. Forward and reverse rate are equal. And the amount of people in a city at any given moment is constant. So we can see 35,000 doesn't equal 100,000. But throughout this equilibrium process, the population of this city stays at 35,000, the population of this city stays at 100. Because whoever is leaving is replaced by an equal amount coming back. Also, the word dynamic means continuous movement. So it's not that we're just sitting at 35,000 people and no one's leaving and no one's coming back. It's dynamic, meaning that there's constant loss and gain of forward and reverse motion. So that word dynamic means constant movement. Okay? So that's another example of equilibrium. So here we have reactants, products, city versus city, forward rate, reverse rate, and then the concentration, meaning how much I have there. Okay, I think I'll stop that video, and then when we come back, we'll look at part 2, looking at the law of chemical equilibrium. So we'll see you soon.